Morning, guys. Today we're going to be doing 6.4b, day 2, special differential equations. Yesterday we did a growth problem, and today we're going to do a decay problem. And remember, when they tell you an amount such as radium, radium in such a way that the rate of decay is proportional to the rate of decay is proportional to the present amount at any time t, the present amount of radium at any time t, we need to use a direct variation equation. If it's proportional to the amount, well, that is the same as it said yesterday, directly proportional to, so the rate of decay is proportional, it's directly proportional to, it's not inversely. So we're going to pick a variable for radium, maybe get a little crafty, call it R, and we're going to write a differential equation stating the relationship between the rate of change of R and the amount of the substance at any time t. So that means my rate of change, dr, with respect to t, dr dt equals my constant of proportionality, remember that k is just going to be a number, times the amount of substance that's left, which is r. And that's the amount that's left. So there is our differential equation. And what we're going to do with this differential equation is we are going to solve this differential equation. So we're going to solve this to find r as a function of time. Well, first thing we need to do is we need to separate variables. So the first thing I'm going to do is mentally I'm going to multiply by dt. So I'm going to say dr equals k times r dt. And we got to get that r over with those r's. So I'm going to multiply by 1 over r dr equals k dt. So I have separated my variables. And if you're like, well, there's a k over there with that dt. No, k is a constant. So now that we've separated, we separate and then we integrate. And when we integrate, the antiderivative of 1 of our r, that's ln absolute value r, equals kt plus c. Please don't forget your plus c. That is your constant of integration. Well, as I keep on plugging and chugging, well, if I want r as a function of t, I need to solve for r, which means I'm going to exponentiate both sides. That gets rid of that. I just have an r, and I can drop the absolute value because I know e to the kt plus c. There's no way to raise e to a power and get it to be a negative number, therefore I can get rid of that absolute value. And remember, that plus c is really r in terms of t equals my c times e to the kt. So there is r as a function of time. Well, notice I don't know what my c value is, but remember that c value is our initial amount. K, our k value in this case, our k is going to be our rate of decay, or our decay factor, I should call it, And we're going to turn around here and we're going to use this and we're going to say what we found before, we found r in terms of t equals some constant e to the k t power. And suppose the half-life of radium 226 is 1,590 years, and suppose a sample has a mass of 80 milligrams. Well, what does that tell me? Well, this is kind of telling me my sample, this is my initial sample. So my initial sample at time 0, means R, the amount of radium I have, is 80 milligrams. Well, what happens if 1,590 years pass by? I guess my R, because 1 half-life transpires, I'm going to have 40 milligrams left. So what are we going to do? We're going to look at these things, and remember, C is the initial amount. Okay, don't forget C is the initial amount. Okay, because what we're going to do is we're first going to use that initial amount because that's going to let us calculate C. Watch, because 80 is going to equal CE. Well, K times anything when T is 0, so I know C equals 80. Well, that takes me to the second step. I used that condition first, and then I'm going to use my next condition, but R in terms of T now is, I know it's going to be 80 E to the KT. Well, I need to calculate K. I need to find K so that I'm actually going to be able to use this. Well, what do they tell me about this? So they tell me R, I have 40. When I start with 80, E, and K, I don't know what K is, but I do know the time is 1,590 years. Okay, so what I'm doing is I'm using my notion of a half-life here, and big shocker, when I divide 40 by 80, I get 1/2 equals E to the 1590K, and now I need to find out what K is. Well, I'm going to have to rewrite this thing so I know logs actually equal exponents, 1590K, and if I'm going to call that a half, I'm just going to go decimal on it. So I know my K value is going to equal the ln of 0.5 divided by 1590. Now remember from yesterday I said if we use this function with this K value, we need to use the exact value. And if we are actually writing, okay, to find the particular solution, my particular solution is kind of ugly. My particular solution is actually R of T equals 80 E, and K is actually the ln of 0.5 divided by 1590 times T. That is my particular solution because at time 0 now, okay, at time 0, I will have 80 milligrams, and also at time 1,590, well, now I'm going to have 40 milligrams. But if we're going to use this, okay, remember, we are going to need to be able to tell our calculator to store this number in there. All right, we're going to store that number in there, and the way we're going to do that is we're going to come back, and if you're like, well, I didn't want to really solve that equation, okay, well, say you didn't want to solve that equation, say you wanted to say menu, algebra, solve, and you wanted to use solver for your 40 equaling 80 E to the, we took that to the 1,590 T, right? Because no, K. I need to, well, yeah, I'm going to leave that K in there, so I got to hit delete, and I'm going to say times K. And what we are going to do is we're going to come over and we're going to say, would you please solve for K? Okay, because we know we put that in there for years. So if I go like that, hey, look, that's just what we had, except we had 0.5. Well, that's the same as the negative ln of 2. Remember, bring that negative up, that's 1/2. But what we really want to do is we want to store our number that we calculated algebraically, or either way you want to do it. We're going to take our ln out here, and I'm going to say, all right, so now I'm going to say control. I have my ln of 0.5, and I'm going to divide that by 1,590. And I'm going to say, oh, there it is. And I can put it in there. Now remember, you hit control there to get the store, because the STO button's up there. We're going to store that, and I'm going to store it in K. All right, I'm going to store that because that's the variable I'm using, and whenever I hit a K, boom, there it is. And if I wanted that K as a decimal to report my findings, I would hit control, and it's negative. Ooh, isn't that nice? K should be negative. And that K value, I just did something wrong in here. Hold on. I thought I did something wrong, but I really didn't. And see, you know, in calculus, we say we always round to 3 decimal places, right? Well, if I did that in this particular case here, I would have to take, because this is scientific notation, I would say 1, 2, 3, 4. There's my decimal point, 0, 0, 0, 4. I couldn't even round that. This is why you're going to want to leave the exact value in there when you're using it, okay? Because we need the decimals. So what we're going to do is we stored that in K. So now we have that value in there. And I have that in there because the next problem they're going to ask me pretty quick here is they're going to ask me what's the mass after 1,000 years. Well, what that's asking me to do, that's asking me to find R of 1,000, okay? And that's going to get me to say 80 e to the k times 1,000, okay? And I know that k value is a number. So I'm going to come back here and I'm going to say R of 1,000 actually equals how much? And now I'm going to type that into my calculator back here because I'm going to say, what do we have? We have 80 e to the k times 1,000, don't we? Another 0, and that's going to give me 51.723 years. Or not years, that's going to give me how many milligrams are there. So I'm going to come back here, and this is going to equal approximately 51.732 milligrams, okay? That is not any calculus involved there. You did those with pre-calc. Plot the graph of the amount of radium as a function of time. That just says graph that. Well, if you remember what your parent graphs start at, and we know this is going to be a decay function, and so I'm going to come up here and I'm going to start my graph up here at 80, and it's going to decay. It's going to it's going to come down, a little something like that, where my amount of radium left in terms of time is going to come across there. Okay, so that's just making a quick graph of that. When will the mass be 30 milligrams? Well, boy, that's kind of tough. So we're going to say, when is 30 equal to 80 e to the k times t? Okay, remember, k is a variable. I don't want to algebraically solve this. This type of problem would be on the calculator active portion of your test. So it really would make very good sense for you to, I just want to clear that out. It would really make sense for you to say menu, algebra, and use your solver to say when is 30 going to be equal to 80 e to the k, and watch, it's going to put it into the bold, times t, and then I'm going to come over and I'm going to say, could you please solve for t? And then I'm going to hit Control Enter, and looks like you'll be down to 30 milligrams in about 2,249.91 years. Okay? And remember, we're rounding, unless it tells you to round to the nearest year, and we're going to say, t is approximately equal to 2,249.910 years. Okay? I have my setup right here. I used solver. Made it a lot easier to solve, but you don't have to use solver if you want to algebraically solve it. You can go ahead and algebraically solve it. It gets a little bit ugly with that exact value of k in there, though, all right? So what we're going to do is we're going to do one more problem here. We're going to do the tin can leakage problem. This one has a little bit different spin. But suppose you fill a tin can with water, then punch a small hole near the bottom of the can with an ice pick. The water leaks out quickly at first, and then more slowly as the depth or height of the water decreases. So basically, we are looking at a cute little can here, and in that cute little can I have some water, and it's filled up with water, and I'm like, oh, and then the water is just kind of dribbling out of it, right? And it can be shown that the rate at which the water depth decreases is directly proportional to the square root of the depth. Okay, well, so we're going to write a differential equation stating the relationship between the rate of change of the depth, which we're going to call height, and the height of the water. Well, the rate of change of water depth, okay? Well, that's kind of like right here. This is the depth of my water, isn't it? We usually call that like the height of my can. So I'm going to say dH dt, the rate of change of height with respect to time, equals, is directly proportional to the square root of the depth. My height actually equals my depth. I defined my height to be my depth, so this is times the square root of h. There is my differential equation that I am relating, because it's equal to the square root of the depth. Well, we're going to keep on a truck in here, and suppose initially the depth of water in the can is 12 centimeters. Okay, so that means t equals 0, h equals 12 centimeters, right? And it's initially draining at a rate of 3 centimeters per minute. Find the constant of proportionality. Whoa, they spun something on me here, and they're saying that the draining rate, okay, the depth of the water, dH dt, is draining at -3 centimeters per minute. Okay? Well, they want me to find the constant of proportionality. Well, my dH dt I wrote before actually equaled k times the square root of h, didn't it? Okay, well, what do I know? Well, I know at time 0, I have a height of 12, right? And that is initially when it's draining at 3. Draining, that's why I said it's negative. It's draining at that rate, so I'm going to say -3 equals my change in height with respect to time. It's draining at that rate equals my constant times, and it's initially, my height is square root of 12. Okay? So I can get all wonky here, and I can say k equals -3 over root 12, and I can just leave it that way. I don't have to simplify that, but if I really wanted to, I could, which is going to give me what, -3 over 2 root 3, which is going to actually give me 6, -3 root 3 over 6, which actually gives me the square root of 3 over 2, but it's negative all the way across there. The square root of 3 over 2. Doesn't matter. To be honest with you, I would have stopped with this one, and I wouldn't have simplified it because I don't need it simplified, really. Sometimes it helps in the problem. As I move along, I'll use this, but it doesn't matter which one I use. Okay. Solve the differential equation to find the depth of water as a function of time. Use the information in part B to find the particular solution. Suppose that the initial depth of water at the can is 12 centimeters and it's initially draining. We did that already. We already found K. So we are at the point of dH dt equals negative the square root of 3 over 2 times the square root of h. That's right where we're at. Okay, well, I need to separate my variables. Well, how am I going to separate my variables? Well, I'm probably going to multiply my dt over here, because then that gets rid of that. And then I'm probably going to say times 1 over the square root of h to get my 1 over square root of h with my h. So then I'm actually looking at 1 over square root of h dh equals negative square root of 3 over 2 dt. And there I have separated my variable. You separate, and then you integrate. Okay? So now that I've separated, now we're going to get the green light to integrate. But before I integrate, I probably want to see this as h to the negative 1/2 dh equaling negative square root of 3 over 2 dt. Well, as I integrate that, what do I get? Well, I get antiderivative of h, it's going to add a half, and I need a positive 1, so I'm going to need a 2 there, right? And then that's going to equal negative square root of 3 over 2 times t plus my constant of integration. And what am I going to do? Oh, now I need to find c. Now I need to find my constant of integration. Well, remember back here, initially the depth of water was 12. So that is time t equals 0, h equals 12. Well, that was kind of nice. So now I can find c, because when t equals 0, I get 0 plus c. Over here, h, well, that's going to be the square root of 12, isn't it? Well, what is the square root of 12? Well, I could leave it that way if I wanted, but it's really, what is that, 2 root 3? So this is going to give me 4 square roots of 3 equals c. So my constant is 4 square root of 3. Okay? And thereafter, our particular solution here. So I've just found c. And what I'm going to do now is I'm going to say, well, okay. So I have basically 2 square root of h. And what I'm doing is I'm coming right here. Okay? And I'm using that. And I'm just pulling my power out. And I'm going to say that equals negative root 3 over 2 times t plus 4 square roots of 3. And now I need to solve this thing for h. I need to get h all by itself. Well, what are you going to do? What are you going to do it? I would probably divide everything by 2 and say square root of h equals negative square root of 3. If you divide a fraction by a whole number, it multiplies the denominator by that whole number, t plus 2 square root of 3. And now what do I, well, I just need to square both sides now, don't I? I just got to come here and square, and I got to come here and I got to square. So h equals negative square root of 3 over 4 times t plus 2 square root of 3 quantity squared. That is h in terms of t. You got it. Okay? You don't have to. Whoa! Oh boy! You don't have to. You don't have to expand this all out. I would stop right there. Okay? You could get crafty and expand that out if you really wanted to, but it's going to get a little nightmarish. Okay? So then what we're going to do here is we are going to plot the graph. We're going to plot the graph of the depth of water as a function over time. Over what values of time does the graph give reasonable values? Well, I guess that means to get reasonable values, we really need to look at our function back here. H equals negative square root of 3 over 2 t plus 2 square root of 3 squared. So, when does it make, what values of t make sense for the height? Well, we know when t equals 0, we know our height equals 12, right? So we already know we're up here at 0, 12, okay? And we do know if we poke a hole in the bottom of the can, sooner or later, that can is going to be empty. So where are my zeros of this thing? Well, let's think about it a second. If I took negative square root 3 over 2 times t plus 2 square root 3, when do you equal 0? When will the height equal 0? That's what I'm looking for. And I would take negative square root 3 over 2 times t. When are you negative 2 square root of 3? I'm going to multiply by negative 2. And that's going to give me square root 3 t equals 4 square root 3. And as I divide by square root 3, I get t equals 4. And I'm going to have to look at that a second. Okay, sorry guys, you weren't screaming at the screen loud enough. I couldn't hear you when you said, Kruger, you rewrote your function wrong. That needs to be a 4 here. And if that's a 4, well, that means this is a 4, which means these are all 4s, right? which means it's going to change that as well, which means as I'm coming through, the first thing I would probably do is multiply by -4. And -4, and then those, oh, I got my 4 there, so 4 kills the 4, that kills my sign, so I have square root of 3, and -4 times -2 gives me positive 8 root 3, and when I divide by the square root of 3, I get 8, so I know when t equals 8, h will equal 0. So I kind of think over here and say, all right, this is when t equals 8, and what is going to happen to my graph? Well, it is going to go something like that, okay? And we want to know, when will the can be half empty? Well, if that's 12, it's probably somewhere here, right, when the height is 6. This, whatever that time is, and it's not going to be half of 8, so we need to find out when 6 equals negative square root 3 over 4t plus 2 square root 3 squared. We want to know what the heck is the time when I'm 6. Well, I really don't want to take this and solve this, so you know what I'm going to do? I'm going to hit pause, and I'm going to type that little bugger into my solver. Why don't you do it at the same time? So I want to solve when is my height 6 equal to negative square root of 3 over 4 times t plus 2 square root of 3 quantity squared. Please solve for t, and I don't want any roots for the answer, so I'm going to hit Control Approximate, and obviously it's going to be a quadratic equation. Okay, and I say obviously, but it might not be that obvious to everybody, but we're looking when t equals 2.343 seconds or when t equals 13.657 seconds. I wonder which one it is. Okay, so now I got to come back and I got to really think about this with my graph. Not really. But when I come back to my graph, it's empty at t equals 8, so it has to be when t is approximately equal to 2.343 seconds. Is it seconds or minutes? I think it's seconds. We poked a pretty good hole in it. Seconds or minutes? Minute, not seconds. Minute. Sorry. It is minutes. That's a pretty fast leak. Minutes. So 2.343 minutes, it will be half empty. So we just barely poked that little guy. Hopefully these make sense, guys. I plan on the next, tomorrow, we're going to be reviewing, and I'll have the answers for the whole review packet. Remember, half of that review packet is AP review just for your knowledge to work on and practice going into the AP test between now and before we start reviewing, to kind of acclimate yourself a little bit. And the first 6 pages are the review assignment for our test, which will be on Monday. So hope you have a good rest of your day. Bye-bye.